then that's it for homework-based problems. I've got two more examples, and then we'll call it a day. So let's go on to the next slide. Oh yeah, sorry, I put my interval of convergence here. I forgot about that. Just remember your interval of convergence is only between -1 and 1. It's going to be the same interval of convergence as it was before you integrated, so integrating is not going to be changing that. Okay, here's something that's going to help you on your homework tonight. And this is also a really cool problem, and I can kind of lead you to some other cool mathematics through this problem. So I think it's all around, it's going to be kind of fun. So example 3, write the first three non-zero terms and the general term of a power series to represent the function f of x equals e to the x plus e to the negative x all over 2. We've actually played with this function a little bit before. It is an important function. I didn't pick it randomly. It is important. But I'll get to that towards the end of the slide, and I'll show you some cool stuff that we can use when we're talking about this function. Okay, so what I'm going to do is if I'm going to try to find a Maclaurin series that describes the function f of x, and what I'm going to do is I'm going to try to break this thing apart into smaller pieces. So for example, looks like the first part of f of x is a familiar function e to the x. Well, I already know a Maclaurin series for e to the x, so why don't I write it? E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial, etc., etc., etc. And actually, using the techniques we developed in the lesson today, I can actually find a Maclaurin series for e to the negative x really quickly. E to the negative x equals 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial, etc. All I'm doing is taking the Maclaurin series I just put on the screen, the one right here, and I'm replacing all of my x's with negative x's. And anytime you have an odd power, that's going to replace that term with its opposite. So x is going to the negative x cubed is going to negative x cubed, etc. The even powers aren't going to change, though, of course. What I could do is I lined these up on purpose. You're going to notice degree 0 terms, degree 1 terms, degree 2 terms, degree 3 terms, whatever. I did that on purpose because I'm going to add these two equations together, because in my original function, we were asked to add e to the x and e to the negative x. So that's what I'm going to do. And the neat thing that happens here is there's a lot of cancellation, or there's cancellation for all of the odd powers of x, and there's doubling for all of the even powers of x. And I can line that up for you so you can see exactly why that's happening. 1 plus 1 is going to give us 2. But then x and negative x, those guys are going to cancel. But then x squared over 2 factorial plus x squared over 2 factorial, that's going to double 2x squared over 2 factorial. Odd powers cancel. Even powers double. Look at the doubling right there. Okay, so we can kind of see that pattern developing when we add e to the x and e to the negative x together. But then on top of that, don't forget that really what we're looking for is e to the x plus e to the negative x over 2. So let's divide everything by 2. And that is going to give me my answer. I have 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial, etc., etc., etc. And so there I've satisfied what they asked for in this problem. I got the first three non-zero terms right there and a general term. So technically this problem is done. But I want to look at it a little bit more. I want you to see the cool stuff that's going on in this problem. Take a look at the Maclaurin series we just got. Take a look at this Maclaurin series that just appeared on your screen. Sorry, I'm just switching to a highlighter here. When we look at this Maclaurin series, it should look familiar. It looks stunningly close to a Maclaurin series that we actually just derived at the beginning of our lesson today. It looks a lot like the cosine of x, except suddenly our signs are not alternating. So now everything's positive, 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 positive all the way along, instead of going positive, negative, which we do for cosine. That's not a coincidence. In fact, it is an important thing that the cosine function is related to the function that we just discovered right now. The function we just discovered right now is called the hyperbolic cosine. By the way, you don't need to memorize anything about the hyperbolic cosine. It is unlikely that you would see anything about hyperbolic cosine on the AP test. However, when you guys all go on to be physics and math majors, you're going to see hyperbolic cosine come up there, especially in physics. It comes up a lot. So this looks a lot like cosine. It's not an accident. This is hyperbolic cosine. You can see it expressed as cosh of x, cosh of x, cosine, hyperbolic cosine of x. Now the hyperbolic cosine, instead of working with a unit circle, you're working with hyperbolas. I'm not going to go into those details, but I will show you a graph of the hyperbolic cosine. What you might notice from this graph is that it looks parabolic in a way. It's not parabolic, but it kind of looks, it has a lot in common with a parabola in terms of its just kind of first glance sort of appearance. And actually what that means is a lot of times in nature, when you see things that look like a parabola to you, they're not necessarily parabolas. In fact, I'm going to show you an example in about 5 seconds where it's something that you see multiple times a week. You probably think it's parabolic. It's not parabolic. It's actually described by hyperbolic cosine. And here it is. Power lines. Power lines, when you look at those, they kind of look like they're parabolas. Actually, any time that you've got a cable that's being pulled down by gravity and it's being held up at 2 points, or a string, whatever, if it's being held at 2 points and then gravity is acting on it, this is actually hyperbolic cosine. It's not parabolic. So it's kind of a cool thing. Another one that I didn't even realize until about a couple years ago, someone mentioned that the St. Louis arch is actually not a parabola. It is hyperbolic cosine. So kind of cool. And by the way, if you guys are ever interested, if you're ever in St. Louis, you guys should go to the top of the arch. There's actually an elevator that takes you all the way up, and it's kind of cool going on like a tiny little elevator that's going on an angle. And there's lots of windows up there. I'm sure some of you guys have been there already, but it's worth going. And plus, if you go to the top, they probably sell t-shirts up there that say, "I rode the hyperbolic cosine curve to its absolute maximum." If they don't sell t-shirts that say that, we should make them. If you guys have any suggestions for the caption, then let me know, but I think that's a good one. I rode the hyperbolic cosine curve to its absolute maximum. Okay, anyway, last example, then I'll let you guys loose. Last one is, it's a little bit abstract, but I think it's important to do. Write f of x in terms of familiar functions without using series. So what I'm going to do is I'm going to give you a function f of x defined in terms of a Maclaurin series. And what we're going to have to do is we're going to have to take that Maclaurin series and work with it and turn it into a set of familiar functions that don't have infinite series involved. Here it is, f of x equals 2x plus 2x to the 4th plus x to the 7th plus x to the 10th over 3 plus x to the 13th over 12 plus ... And then here's a formula for a general term, 2x to the 3n plus 1 over n factorial. Now, oftentimes with sequences and series, I like to look at the first however many terms I can list, first, 2, 3, 4, 5 terms, and look for a pattern. There is a pattern in these terms, and you could find it, and you guys, you might have already figured out what it was, I'm not sure. However, for me personally, looking at the first few terms of this Maclaurin series is not very helpful to me. I think trying to find the pattern could sometimes be very difficult, and instead what I'm going to do, I think that the key to this problem is taking this general term they gave you and working with that. So I'm going to rewrite this Maclaurin series as, in summation notation, the sum from 0 to infinity of 2x to the 3n plus 1 over n factorial. And what I'm going to do is I'm going to take this general term and I'm going to try to manipulate it. I'm going to do some algebraic manipulations on this and try to turn this, this infinite sum into a sum that's more familiar to me. First trick I'm going to use is that x to the 3n plus 1 is actually the same thing as x times x to the 3n, right? That's x to the first power times x to the 3n. And then actually that's going to allow me to factor some stuff out from my sigma, from my summation notation. Here's what I mean. If you take a look, I've got this 2x going on here. And that 2x does not involve n in any way. And so actually, I could treat this kind of like a constant being factored out of a set of parentheses out of, any sort of algebraic expression. I'm going to take that 2x and I'm going to factor it out. Now, the reason I'm allowed to do that is the 2x doesn't involve n in any way. And so since it doesn't involve n, and n is what is the sum is indexed by, I can actually just take it out, just like a scalar. I'm basically factoring out a scalar. So here we have it, 2x times the sum from 0 to infinity of x cubed to the nth power all over n factorial. And actually you'll notice I have one other little change here. X to the 3n, I rewrote that as x cubed then to the n power. And the reason I did that is hopefully what you guys are noticing already is the inside of this sum looks really, really close to our sum for e to the x. In fact, it only differs by that x turning into an x cubed. And so really, that sum is, it's not e to the x, but e to the x cubed. So hopefully you guys can see that right there. This x cubed is now, when we work this all out, we have e to the x cubed rather than e to the x. Just kind of a little substitution trick there. And then you guys can see we still have that 2x. So really all we did to finish up this problem is 2x times this infinite series is the same as e to the x cubed, and we're all done. We satisfied the goal for this problem. We wrote f of x in terms of familiar functions that did not use infinite series. And there we have it. So anyway, guys, I hope the lesson went well for you. Remember that you can always pause this, rewind this, listen to things again. The other thing is I'm hoping that we'll be back in class together on Thursday, but you never know what can happen with weather or with power outages or whatever. I mean, all things are possible with weather. And so if we're not in school on Thursday, the remote possibility that we're not in class on Thursday, check the website again, and I'll have assignment information for Thursday if it does become relevant. But other than that, just stay caught up with the syllabus, and please do the homework that's assigned for this evening, and I will hopefully see you guys on Thursday. Bye-bye. Oh, by the way, guys, be careful when you're driving and such. Don't want anyone to get hurt. It was pretty treacherous even just driving home from school when the storm had started. Okay, bye.